And hello, welcome YouTube to this video on OpenFoam. The last video we're talking about increasing the time step so that we can get a stable solution. However, as I ran the simulation yesterday, I again ran into a problem where again this error comes out, which is a numerical instability. You can see the delta t going smaller and smaller. Okay, why is that so? Now, if you scroll a few time steps before, we will see that, prior to this, let's see, somewhere here is where the delta t is still relatively stable, 0.000839. Okay, 83 something. So this is a stable time step. Now, what happened was, if you take a look at the maximum Courant number, I kept it at 0.002 or 0.02, and the diffusion number, the sphere diffusion number, which is to do with the conduction, everything, it gets smaller and smaller. But suddenly, as this 0.02 limit is being enforced, okay, you see the delta t is going smaller, but the max Courant number is actually growing. So OpenFoam tries to compensate by changing the time step smaller, and because of that, then you have all these numerical instabilities associated with small time step. Okay, so basically, trying to keep your max Courant number at 0.02 does not really make sense. Usually 0.5 is enough. If you want to do a pinpoll simulation, you can even go more than 1. That's fine. Okay, so yeah, the Courant number here is trying to be kept at 0.02, which is far too stringent. We might want to go for something a little bit bigger. Okay, so we already have some data here. That's fine. Okay, so I'll go to k omega SST IDDES. Okay. Let's see, CD core smash k omega SST IDDES. Okay, one more time. Okay, here I am. It's 36 seconds of time being simulated. Okay, so what I'll do is just change the control dictionary. Okay, to change the max Courant number from 0.02, as you see over here, to 0.5. Can't remember why I set it as such a low number, but once I start running it, you can just run CHT multi region foam and to run it in the background, and now it's working again. So you can see where at this setting, the max Courant number becomes 0.18 and the max diffusion number becomes somewhere around 10, and the simulation becomes relatively stable, so to speak. Now if you're running a Linux Mint or Ubuntu, you are able to sort of use this window still. I mean, this terminal window is kind of going by very fast because of the simulation. But what you can do very simply is just to click a new tab, and you'll conveniently be brought to the same place, and that process is running in the background. You can check anytime to see its output, so that's very good for us. Okay, so now we can so-called wait for the results, so to speak. And you can do the same thing, like I'm using this command watch sensors. Okay, and this whole window will be used to monitor the temperature of the computer, which by the way now is pretty high. It's about 92 degrees, which is a little bit too high for comfort, but I guess for short bursts that is fine. Alright, now usually what I like to do to lower the core temperature is of course run it in parallel, and running it in parallel of course means distributing the load over several cores rather than putting all that load on one core and making it work really hard. Okay, of course the core that is hot tends to change from time to time. Okay, now I'm not sure exactly if it works for Windows subsystem for Linux, whether you can do this new tab kind of thing. I believe Windows has its own terminal program where you can use Windows subsystem for Linux or any terminal based thing in multiple tabs like this for convenience, right? So that's just a convenience perk. It's not strictly speaking necessary to do this. You can just open new windows if they are getting too overcrowded, but this I believe is useful, especially when you want to edit files, and of course take note of temperatures like this. Now, so let's see. Yeah, so now maybe we'll want to start fiddling while waiting for the results. Maybe one thing we can do is to take a look at existing results, of course. We can take a look at existing results. Alright, so look, it's already at 50 seconds. So how long am I running this for? Let's see, control dictionary. Okay, end time is about 300 seconds, so it should be done pretty quickly. It's a very short burst. Okay, so shouldn't be too much of a concern over here in terms of time frame. Alright, so yeah, let's take a look at the post-processing, and we can see the average heat transfer coefficient, if there's anything over there. Okay, I do have some data over here. Okay, you have a average temperature and some heat transfer coefficient over here. Okay, again we have some heat transfer coefficient over here, about 90 something, 100 and something, give or take. Now how does that actually compare? Okay, how does that actually compare? So let's go to our hot sphere and oil, and then we take a look at our results analysis. Now this thing is in Excel. Now I'm using LibreOffice to open it up. Okay, so what do we have? Okay, so we have the heat transfer coefficient. Heat transfer coefficient of let's say this is a fine mesh, okay, with the correct thermophysical properties of let's say what do you call that? Dalthum, yeah, Dalthum oil. And this one is the coarse mesh one. You can see that our heat transfer coefficient is about 90 something, okay, which is quite characteristic of coarse mesh, because we were just trying to make sure the whole thing was stable. Okay, so if I look at surface field value .dat data, it's about 90 something. Okay, the heat transfer coefficient is about 90 something. We take a look at a thermophysical property, the laminar case. We also realize it's actually somewhat higher than what we get over here in the laminar case. Okay, so this turbulence modeling does help a little bit in terms of increasing the heat transfer coefficient. Now, however, it does not perform as well as the fine mesh with laminar calculations. So honestly speaking, if you take a look at the CFD CFD fine mesh case, we use a fine mesh to do this laminar what do you call that, simulation. we did not put a turbulence model in. Actually, it matches relatively close if you compare the Nusselt versus the Rayleigh number, and of course the temperature. You do a sort of that comparison. Okay, if you do that, it is actually matching pretty well with the Rayleigh number there. So if you plot Rayleigh number, as I did in the last few videos, if you plot the Rayleigh number, as we do in the last few videos against the Nusselt number, you'll see that it actually matches pretty well with the empirical correlation. Honestly speaking, that is good enough, and you don't really need a turbulence model already. Having a turbulence model would increase the amount of heat being transferred, because you increase the turbulent thermal diffusivity. But as you can see here, for much of this case, where is it? Yeah, for much of this case, the Rayleigh number is actually lower than 3 times 10 to the power of 8. Okay, 3 times 10 to the power of 8 is where the laminar to turbulent transition actually happens. So that's why I kind of highlighted it in green here. Now, if we take a look at the fine mesh case, okay, we look at the fine mesh case. Okay, fine mesh case, the 3 times 10 to the power of 8. That only happens for like the first, give or take, I don't see a time step here. Okay, let's see. Okay, I'm looking for the time step, so I want to see what's the... Okay, so 3 times 10 to the power of 8. And what's the Nusselt number, and what's the heat transfer coefficient? This is surface temperature is 416 degrees C or Kelvin. Yeah, so it's a 500 Kelvin and 300 Kelvin. So where's it? Average area temperature 416. Okay, it's around here. So in effect, the turbulence only lasts for the first 10 to 12 seconds. Everything else, you kind of pass below into the laminar regime. So putting a turbulence model there doesn't really seem to make sense. Okay, but as with every CFD simulation, the most important thing is to compare it to experimental data, and that actually is best shown when you actually compare it to an empirical correlation, which is based on experimental data. Okay, so we can see that if we just do a comparison with the coarse mesh, we see that the heat transfer coefficient increases quite a bit compared to the coarse mesh. Okay, but it's not as accurate as, say, having a fine mesh. Alright, it is. You can see the heat transfer coefficient is increasing. Sometimes it's like at 88 seconds is about 98 watts per meter per Kelvin. So give or take. Yeah, let's see this. How much? Yeah, I'm looking for the coarse mesh. Yes, 98 seconds, thereabout. Oops, 90. We have a 95 seconds here. Yeah, heat transfer coefficient is about for the laminar case, about 90, and over here it's like 98. So you can see that the model actually helps increase the heat transfer coefficient artificially, but I mean, anything beyond the 12-ish seconds at this kind of temperature, you won't expect to have as much turbulence and the mesh is so coarse that you're not modeling it right anyway. Okay, but of course you should be able to run a fine mesh version as long as your time step is forgiving enough so as not to introduce all these numerical errors. Okay, so yeah, this is just some comparison for you to take a look at. Alright, now okay, so yeah, anyway, there's something else since the program is running that I want to show you. It is how to do parallel CHT multi-region foam, because that's actually a little bit more complicated than running in parallel for, let's say, buoyant pinball foam, because of course you have multiple regions and now you need to decompose each region out. So I have a test case called coarse K omega SST IDDES parallel. I just copied that over from this file, just doing a CPAR. Actually, on second second thought, I want to change this into something that is fine. Okay, I want to change this into a fine case, then I decompose. Because I mean, if you have more cells, it makes more sense to split the processes and everything. So let's go to fine K omega SST IDDES parallel. Okay, we can do an all clean first, and we'll just do an all run serial pre, which is helping us to mesh the thing. Oh, speaking of meshing, I need to change some parameters in SnappyHex Mesh. Okay, SnappyHex Mesh dictionary. I want my refinement level now to become 2. 2, and I want to have this refinement region called refinement cylinder. Okay, so let's do that again. All run. Oh, let me change the control dictionary to. That will become a max Courant number of 0.5, just like we were talking about just now. Okay, and this should be able to run in serial. So wait for SnappyHex Mesh. It should be able to finish in about 18 seconds. Then let's try running our usual decompose parallel. You will see that it doesn't quite work the same way as buoyant pinball foam, and it will start asking you for extra things. Okay, so let's do a decompose parallel. So again, you look at this. We'll have 4 processes, because if you take a look at the decompose parallel dictionary, we will have 4 subdomains, and we use the Scotch method. Scotch method means you don't have to care about all of these. Right? You don't have to care about all of these things here. Okay, so since that is the case, if we take a look at processor 0, for example, it will have the 0 file, it will have the constant file, but none of these files will have regions in them. Okay, so that's a little bit problematic. Okay, that's a little bit problematic. And how are we then supposed to make sure all the regions go in? So if you go to our foam tutorials under heat transfer, you can go to CHT multi-region foam. I'm going for the external coupled heater. If we take a look at that all run file, okay, we can see that we use decompose parallel on all regions. Okay, the rest of the things you kind of these are like redundant, not redundant, but they are for what do you call that? They're for the external solver, and these few lines of code here, if you want to run it in serial. Okay, but they tell you to do this. Run decompose par on all regions. So let's try running decompose par on all regions. Okay, so yeah, that's on the right track, but Okay, my time is almost up. I don't want to take too long, but you can take a look here. It's supposed to decompose two regions now, the oil and the sphere. And it's saying, well, I want to decompose the oil mesh. But it says there's an error because you can't find the file in Decompose Parallel Dictionary under System Oil Decompose Parallel Dictionary. That's where it's supposed to be. Okay, so there are a few settings we kind of need to do to get this to work. Alright, so we'll talk more about that in the next video. And of course, we'll leave the other file to run. It's about halfway through now. 161 seconds. It seems to be quite stable when we increase that timestamp. Okay, so see you guys again. Bye bye.